Have you ever wondered what lies at the heart of the universe, hidden in the shadows, defying our understanding of physics? This question has intrigued humanity for centuries, leading us to probe the mysteries of the cosmos, the most enigmatic of which are black holes. Black holes, these celestial entities, are not merely holes in space, but rather they are concentrations of mass so dense that they warp the very fabric of space and time around them. They are the universe's ultimate vanishing points, where anything that ventures too close, be it matter, light, or even time itself, is swallowed whole, never to return. They are cosmic conundrums, entities so extreme in their nature that they push the boundaries of our understanding of the universe. They challenge our grasp of physics, requiring us to rethink and revise our theories and models. At their core, or singularity, the laws of physics as we know them break down. Here, space and time become meaningless, and all our scientific theories fall short of explaining what truly transpires. Black holes also serve as cosmic laboratories, allowing us to study the effects of extreme gravity. By observing the space around black holes, we can gain insights into the behavior of matter and energy in conditions that cannot be replicated on Earth. Our journey to understand these cosmic phenomena has been long and arduous, filled with both triumphs and setbacks. It has led us to question our understanding of the universe, to push the boundaries of human knowledge, and to peer deeper into the fabric of reality. These cosmic monsters, known as black holes, are the enigma we will unravel today. Join us as we embark on this journey, venturing into the heart of darkness, into the realms of the unknown, to shed light on the mysteries of black holes and the universe. But how does a black hole come to life, you might wonder? Well, let's embark on a journey back to the birth of a black hole. Like many great tales, our story starts with a star, but not just any star. This is a star that's at least 20 times the mass of our own sun. For most of its life, this star maintains a delicate balance, with the force of gravity pulling inwards and the energy from nuclear fusion pushing outwards. However, this balance cannot last forever. After millions or even billions of years, the star exhausts its nuclear fuel. Without the outward pressure from fusion to counteract gravity, the star begins to collapse under its own weight. This collapse triggers a cataclysmic event known as a supernova explosion, outshining entire galaxies for a brief period. Yet not all remnants of the star are blasted away in the supernova. The core remains shrunk and incredibly dense. If the core's mass is great enough, no known force can prevent it from collapsing further. It is at this point that our star's fate is sealed, and a black hole begins to form. The core collapses, shrinking smaller and smaller, until it forms a point of infinite density known as a singularity. Around this singularity, gravity is so strong that nothing, not even light, can escape its pull. This forms a region of space we call the event horizon, the point of no return. Inside this event horizon, the laws of physics as we understand them cease to apply. Space and time become intertwined and distorted. All paths lead towards the singularity, and destruction is inevitable. It's a place of mystery and wonder, where our understanding of the universe is pushed to its limits. And thus, from the ashes of a dead star, a black hole is born. Now that we have witnessed the birth of a black hole, let's delve into its anatomy. A black hole, in essence, is an object of such immense gravitational pull that not even light can escape its clutches. This is a realm where our normal understanding of physics seems to break down, and new, more exotic rules come into play. The boundary of a black hole, the point of no return, is known as the event horizon. Imagine it as an invisible sphere around the black hole. Once you cross this boundary, you are inexorably drawn into the black hole. No rocket, no matter how powerful, can pull you back. Inside the event horizon, all paths lead to a point known as the singularity. This is the heart of the black hole, where the object's entire mass is crushed into a point of infinite density. This is where space and time as we know them cease to exist. The singularity is hidden from the outside universe by the event horizon, a cloak of invisibility, if you will. Surrounding the black hole is a swirling vortex of gas and dust, known as the accretion disk. This matter is slowly spiraling into the black hole, like water going down a drain. As it falls in, It heats up and emits a brilliant glow, often outshining all the stars in the host galaxy. This is how we detect black holes, by the light of their accretion disks. Black holes, despite their name, are not empty holes. They are packed full of mass, which gives them their powerful gravitational pull. They are the ultimate cosmic vacuum cleaners, gobbling up anything that strays too close. So there you have it, the anatomy of a black hole, a boundary from which nothing can escape, a point of infinite density at the heart, and a glowing vortex of doomed matter spiraling in. In the heart of a black hole lies a point of infinite density, the singularity. Imagine a force so strong that not even light can escape its clutches. The power of gravity, an invisible yet omnipresent force, is indeed such a phenomenon. It's the glue that holds our universe together, binding planets to stars, stars to galaxies, and galaxies into colossal cosmic webs. But nowhere is the power of gravity more evident or more extreme than in the vicinity of a black hole. To understand gravity's role in black holes, let's take a step back and think about an apple falling from a tree. This everyday event is driven by the gravitational force between the Earth and the apple. Now, if the Earth were to suddenly shrink, keeping its mass constant, the apple would experience a stronger gravitational pull and fall faster. This is because gravity increases as objects get closer. Now picture a black hole. It's like the Earth in our apple scenario, but condensed to an almost infinitesimally small point, a singularity. This singularity, despite its minuscule size, contains a mass many times that of our Sun. The result? An unimaginably extreme gravitational field. So intense is this gravitational force that it warps the very fabric of space and time around it, creating what we call an event horizon. This is the point of no return. Beyond this boundary, the gravitational pull is so strong that nothing, not even light, can escape. That's why black holes are, well, black. They swallow up everything, including the light that would allow us to see them. It's also worth noting that the closer one gets to a black hole, the stronger the gravitational pull. This results in a phenomenon known as spaghettification. If you were unlucky enough to stray too close to a black hole, you'd be stretched vertically into a long, thin shape, like a piece of spaghetti, while being compressed horizontally. A rather unceremonious end, wouldn't you agree? In the world of black holes, common notions of space and time cease to apply, and all the rules are written by one force: gravity. It's a stark reminder of the power it holds over our universe. In the vicinity of a black hole, gravity rules supreme. Have you ever thought about time travel? Black holes might be the closest we ever get. Picture, if you will, a world where time doesn't tick away at a constant rate, a place where the seconds stretch and warp, where an hour can stretch into a day, a week, or even a year. This isn't the plot of a science fiction novel, but a very real concept in the realm of astrophysics called time dilation. Time dilation is a fundamental aspect of Einstein's theory of relativity. It tells us that the passage of time isn't a constant, but something that can be altered. According to this theory, the stronger the gravitational field, the slower time passes. And where do we find the most potent gravitational fields? Around black holes. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They are the ultimate time distorters, the epitome of gravitational power. A clock near a black hole would tick slower than a clock further away. This is not because the clock is broken or affected by the black hole's gravity, but because time itself is being stretched. Imagine standing at the edge of a black hole, watching a friend venture closer. As they approach the event horizon, the point of no return, you'd see them move slower and slower until they seem to freeze in time. But for your friend, time would be passing normally. This is the mind-bending reality of time dilation near black holes. Of course, venturing near a black hole for a time-bending adventure isn't really feasible or advisable. The immense gravitational pull would stretch and squeeze you into a long, thin shape, a process unceremoniously named spaghettification. Not the most pleasant of travel experiences, I dare say. So, while we might not be packing our bags for a black hole vacation anytime soon, the concept of time dilation gives us a fascinating glimpse into the strange and counterintuitive nature of our universe. Near a black hole, time slows down, blurring the lines between reality and science fiction. Black holes could be cosmic shortcuts to distant parts of our universe. A tantalizing idea, isn't it? The concept of wormholes, tunnels in space-time, has captured the imaginations of scientists and science fiction enthusiasts alike. But what is the connection between these theoretical constructs and the fascinatingly elusive black holes? Let's start by exploring what a wormhole is. A wormhole, as per theoretical physics, is a hypothetical structure of space-time envisioned as a tunnel connecting points that are separated in space and time. Picture it as a subway system for the universe, allowing one to bypass the vast cosmic distances and jump from one end of the universe to another almost instantaneously. Now, where do black holes come into play? The answer lies in Einstein's theory of general relativity. According to this theory, a black hole is a region in space where gravity is so strong that nothing, not even light, can escape its pull. This intense gravitational force warps the fabric of space and time around it, creating what we know as the event horizon. It's this warping of space-time that has led some theorists to propose that black holes could in fact be linked to wormholes, but it's not as straightforward as it sounds. The insides of black holes are predicted to be singularities, points of infinite density, which the current understanding of physics can't describe. So, while a black hole may theoretically be a doorway to a wormhole, stepping into one might not be a pleasant journey. It's like stepping into the unknown, or perhaps the unknowable. Moreover, the wormholes, if they do exist, are predicted to be highly unstable. They may collapse instantaneously, making it impossible for anything to pass through. However, some theories suggest that exotic matter with negative energy could potentially stabilize a wormhole. So, could black holes be gateways to other galaxies? The answer lies in the realm of theoretical physics. It's a question that has yet to be answered definitively, and one that continues to inspire awe and wonder in our quest to understand the mysteries of the cosmos. Black holes might be invisible, but they are not silent. It's a statement that might seem counterintuitive, considering that sound can't travel in the vacuum of space. But when we talk about the sounds of black holes, we're really talking about the rhythm of the universe, the ebb and flow of cosmic energies, and the reverberations of gravity itself. Now, here's a fascinating fact. Black holes contribute to these cosmic ripples, these gravitational waves that echo through the universe. And how do they do it? When black holes collide, they create ripples in the fabric of space-time, much like tossing a stone into a pond. These ripples are gravitational waves, and they carry with them the signature of their mighty creators. But how do we hear these gravitational waves? That's where the ingenuity of human science comes in. We've built detectors like the Laser Interferometer Gravitational Wave Observatory, or LIGO for short, which can pick up the faintest whispers of these cosmic waves. These detectors translate the waves into sound, and voila, we have the symphony of black holes. Each black hole collision creates a unique chirp, a crescendo of sound that rises in frequency and intensity as the black holes spiral closer and closer together until they finally merge. Imagine the grandeur of such a moment. Two astronomical titans dancing their final waltz, their music reverberating across the cosmos. But these gravitational waves do more than just create a celestial soundtrack. They are a window into the universe's most enigmatic phenomena, a means of studying black holes and other cosmic events that would otherwise be invisible to us. They are a testament to the power and majesty of black holes, these silent, invisible behemoths that nonetheless make their presence known in the most dramatic of ways. Through gravitational waves, black holes announce their presence in the cosmic symphony. They are the silent maestros of the universe, conducting a symphony of gravity that resonates across the cosmos. And we, with our detectors and our curiosity, are privileged to be part of the audience. Black holes bend not just space, but time itself. Imagine space-time as a vast, flexible sheet. A marble on this sheet would create a minor dip, representing the gravitational pull of a celestial body like a planet. Now think of a black hole as a bowling ball on this sheet. It doesn't just create a dip, it warps the sheet to an almost inconceivable depth, distorting the space-time around it. But what does this mean? Well, let's delve a little deeper. According to Einstein's theory of relativity, the force of gravity is a result of this curvature of space-time. When a massive object like a black hole distorts space-time, it creates a gravitational field so intense that nothing, not even light, can escape its grasp. This is why black holes are invisible to the naked eye. This warping of space-time also influences the passage of time. Near a black hole, time slows down. This is not a mere science fiction trope, it's a phenomenon known as time dilation. If you were to watch a clock falling into a black hole, it would appear to tick slower and slower the closer it got to the event horizon, the point of no return. From the clock's perspective, however, time would seem to pass as normal, and here's where it gets even more mind-bending. Inside the black hole, the very fabric of space-time becomes twisted to the point where the usual rules of geometry no longer apply. Space and time switch roles. Instead of space being something you move through while time marches inexorably forward inside a black hole, space itself drags you towards the singularity, the black hole's core, while time becomes a space-like dimension you can move through. All this goes to show that black holes are not just destructive forces of nature. They are cosmic phenomena that challenge our understanding of the universe and the very nature of reality itself. Black holes, the cosmic artists, sketch their influence on the canvas of the universe. What would happen if you fell into a black hole? Well, it's a question that has been asked by many, from curious minds to seasoned astrophysicists. And the answer is as fascinating as it is terrifying. The experience is known as spaghettification, a term coined by British astrophysicist Sir Martin Rees. Imagine this. As you approach the black hole, the difference in gravity between your head and your feet would become incredibly extreme. This is due to the intense gravitational pull of the black hole, which increases exponentially the closer you get to it. Your body would start to stretch, becoming longer and thinner like a piece of spaghetti. Hence the term spaghettification. The process would be, needless to say, lethal. Your body would be torn apart long before you reach the singularity, the core of the black hole. But let's not stop at the physical. What about time? As you fall into a black hole, you'd experience time in a drastically different way. Due to the immense gravitational pull, time would slow down for you. To a distant observer, it would seem as if you're falling forever, while you, on the other hand, would experience your demise in a matter of moments. You'd be stretched into a long, thin strand of atoms, swallowed by the cosmic beast that is the black hole. As you cross the event horizon, the point of no return, you'd see the universe outside warp and distort due to the extreme bending of space-time. But don't fret. The chances of us coming close enough to a black hole to experience this gruesome fate are astronomically low. You are more likely to win the lottery while being struck by lightning than to be spaghettified by a black hole. So what would happen if you fell into a black hole? In short, you'd be stretched, distorted, and ultimately destroyed. But remember, this is all based on our current understanding of black holes, and the universe has a way of surprising us. A journey into a black hole is a one-way trip, a plunge into the unknown. Our understanding of black holes is still in its infancy, but the future holds promise. Indeed, black holes, these cosmic enigmas, have been the subject of fascination and research for decades. Despite the mystery that shrouds them, we're making strides in understanding their nature and role in the cosmos. In recent years, the Event Horizon Telescope project captured the first ever image of a black hole, a monumental achievement. This image, a fiery ring encircling a circular abyss, has provided us with invaluable data and confirmed many of our theories about these celestial beasts. Furthermore, advancements in gravitational wave detection have opened new avenues for black hole research. With the detection of ripples in the fabric of space-time caused by cataclysmic events, such as the merging of two black holes, we are now able to hear these cosmic giants in a way never thought possible. Looking to the future, scientists are hopeful about the prospects of multiverse theories and the role black holes could play in them. Some suggest that black holes might be portals to other universes, a concept that, while speculative, is tantalizing. Moreover, the exploration of quantum gravity, a theory that seeks to reconcile quantum mechanics with general relativity, could shed light on the intriguing paradoxes that black holes present. This includes the information paradox, a conundrum that revolves around what happens to the information about the physical state of things that fall into a black hole. The future of black hole research is also intertwined with the development of more sophisticated telescopes and detection instruments. With them, we might be able to gather more data about these fascinating celestial objects, thereby offering us a more profound understanding of the universe. As we continue to gaze into the abyss also gazes back at us. And as it does, we inch closer to unraveling the secrets it holds. The future of black hole research, though filled with uncertainties, is undoubtedly exciting. It is a journey into the unknown, a testament to our insatiable curiosity and our relentless pursuit of knowledge. So we've journeyed to the heart of the universe, delved into the enigma of black holes. We've taken a cosmic voyage to explore the birth, anatomy, and profound mysteries of these fascinating celestial objects. We started with the birth of a black hole, the violent death of a massive star, culminating in an explosion so powerful that it compresses the core of the star into a singularity, a point of infinite density. This singularity distorts space-time around it, forming a black hole, an entity that not even light can escape from. We explored the anatomy of a black hole, the event horizon that marks the point of no return, the singularity at its heart, and the accretion disk of superheated matter spiraling into oblivion. It's a cosmic monster, a place where our understanding of physics breaks down. We discuss the power of gravity, how it bends space and time around a black hole, causing time dilation, a phenomenon where time slows down near a black hole. We explored the concept of wormholes, theoretical bridges that could connect different points in space-time, possibly even different universes. We listened to the sounds of black holes, the eerie hum of space-time being twisted and warped, a testament to the unimaginable power of these cosmic entities. We touched on the concept of spaghettification, the bizarre and terrifying fate that awaits anything that falls into a black hole. We looked ahead to the future of black hole research, the exciting discoveries that await us as we delve deeper into these cosmic mysteries. With new technologies and a growing understanding of the universe, we stand on the brink of a new era of discovery. And so, as we conclude our journey, we're left with a profound sense of awe and wonder. We've glimpsed the edge of the known universe, peered into the abyss of a black hole, and touched the fabric of space-time itself. Black holes, the final frontier, remain a testament to the wonders of the universe and our quest to unravel its secrets.